Recording.
Yep. So remember last class, we drew cobwebs to understand the stability of fixed point, isn't it? If the cobwebs we drew like go up, move right, come down, goes sideways, again move up, it's a repetitive pattern, and see how the trajectory is approaching. Then if it was going to a single point, we say the fixed point, it is approaching the fixed point and it is stable. Now, if however close, I think Mr. Sangamesh also told last class to take different initial conditions and see whether it is approaching. It did not approach, rather it diverged, however close I take. Okay, so that showed that it was unstable. So yeah, that's the case. Now let us see something more about this. Consider this diagram. Consider this diagram over here, okay? Just a qualitative diagram here, nothing more. So xn, you have xn plus 1, you have it here. You remember what is xn plus 1? It is r into xn into 1 minus xn. This is the logistic map, well known. So what I am doing is I am plotting xn versus xn plus 1. Okay. So it will be just a parabola because rx minus rx square, it's just like a parabola. So if you draw it, let me draw with a different color. It will have this one hump structure. It is not intuitive, but it is intuitive in the sense that yes, it is just like coming from a quadratic nonlinearity here, and then it's a 2 power, so it's a parabola. Then you draw this y equals to x line. This is y equals to x line, and this is the curve you have. Fine. I ask you, like if you check the slope over here, if you check the slope over here, if you check the slope over here, the slope is equals to -1. Isn't it? Fine with you? The slope will be -1. And in this slope, let me tell you, draw a cobweb diagram for this. Okay, let us draw a cobweb diagram for this structure. Let us take green, maybe no, CM. So yes, so let us start with an initial condition. I have marked x naught over here. Okay, I think red color would suit. So red color. So let us take. So what should the cobweb do? I should go, since I chose an initial condition, I should go vertically upwards. Let us go vertically upwards. So yeah, somewhere here it hit. Then what should I go do? I should go to the horizontal direction, and it hit y equals to x. Since it hit y equals to x, my job would be to come down. My job would be to come down. Okay. I did not draw a good figure, but maybe I can make it up. Think it is like this. So when this comes, it collides here to the tangent point. Okay. Then again, if you go back, it will hit here. Okay. So this constitutes something like a repetitive structure. Again, if it hits here, again you can go again and fall on this trap, fall on this loop. Okay. But what is this loop all about? This loop is something known as a period 2 orbit. Isn't it? It is a period 2 orbit. If it is a fixed point, you wherever you start, you will like go on like this till you approach something. This is a fixed point. This is how cobweb will approach a fixed point. But if you have a periodic point, cobweb, whatever initial condition you take, at one initial point it will come closer to this and maybe repeat itself on this loop. Okay, so that's how it's a period 2 orbit. If you have a period 4 orbit, how it will look? You can start from here, go like this, and it will again loop over here. Okay, maybe, yeah, just like this. I'll draw again. Yeah. So any initial condition you start, it goes like this. Okay. Comes back. Can you see it's a period 4 orbit now? Okay. The way it will find it out, like the way it will cross each other. So therefore, to actually, if you could have done some coding already, which I shared to you before, then you can easily pick this out that this is a period 4 orbit and this is a period 2 orbit. So therefore I shared the code with you on Colab. So for you to try with different periodic points in logistic map and see how the cobweb looks. So therefore, this is a period 2 orbit. You could have easily catched the visualization just by looking at it. And yes, this is a period 2 orbit. Okay, if you would have worked on the code. Okay, so therefore I strongly suggest where there is a period 2 orbit, put the parameter value that r equals to that in the cobweb code, take any initial condition and convince yourself that the period 2 orbit will exactly look something like this. Okay, and a period 4 orbit will look something like this. All right, so this only will come through experimentations. Therefore I ask you to, I did for fixed points, then I did for chaotic orbit how the cobweb looks. I ask you to do for various periodic point how it looks. I already shared the code. All right, so the period 2 orbit looks like this. That's the idea. But notice a fact that the f prime, the slope at that point is -1. The slope is -1. Okay, so that is a condition for period doubling. So this period 2 orbit was born from a fixed point. I just showed the bifurcation diagram, isn't it? It was like this, then it somewhat like this. Yes. So from period 1, it went to period 2. From period 1, it went to period 2. Now, how it happened? We saw that from the stationary pattern, it went to oscillating. So this is a bifurcation. This is a bifurcation happening. The point where qualitative change occurs is known as a bifurcation. And this is a bifurcation happening here. What kind of bifurcation it is? You had period 1 on the left. After R is changed, it doubled, period 2. So it is known as a period doubling bifurcation. A doubling happened. Okay, period is doubled. So it's a doubling bifurcation. And that happened when slope is equal to -1. Okay. That happens when slope equals to -1. Now, when the slope is not equal to -1, this doubling can never happen. Okay. This doubling only happened because the slope was -1. Now, can you make yourself realize this, that it depends on the slope. If you have a period 2 orbit, okay. If you vary the parameter r, this curve, the green curve will change its look. The green curve will change the appearance, how it looks. Okay. Then the tangent will also change accordingly. So therefore, it might not be -1. So therefore, you might not get another period doubling. But if you have period 2 and you increase the parameter, we saw that there is a period 4 orbit coming in. Okay. So therefore, that means there will be a case where again, if you draw a tangent, it will be slope -1. Then again, another doubling will happen of period 2, again to period 4, again to period 8, 16, all this. Okay. So this is a very intuitive knowledge, very intuitive idea about period doubling bifurcation. When a period doubling bifurcation occurs. Okay. Otherwise, there is a very big theorem where they show that these are the conditions and this is where period doubling will occur. Okay. But I wanted you to know analytically that this is a period 2 orbit. And here you saw that the slope was -1. So where you see a period doubling occurring, there the slope is getting -1. Okay. So intuitively you can analyze that now, that when period doubling will occur when the slope is -1. Okay. Well, you can say what happens when the slope is 1. It is a different kind of bifurcation. Okay, I'll tell you that. So I hope this is at least somewhat to write it more clearly. F prime, maybe this here, F prime at x star is equals to -1. Okay. And this is where period doubling occurs. In higher dimensions, this is just a one-dimensional system. Therefore, you are having derivative at your hand. Now, if you go to two-dimensional systems, which will be in the next class, then you will see that the matrix will come into play. Matrix will come into play. Then you need to compute the Jacobian matrix. The eigenvalue will determine the stability of the fixed point. Okay, in two-dimensional systems, eigenvalues determine the stability of fixed point. Since it is one dimension, the derivative will be sufficient to you. Okay. You will just have a one-dimensional matrix here, 1 cross 1. That is just a number in 1D systems. But the moment you go to two-dimensional systems, you will have a 2 by 2 matrix. Okay. You will have two eigenvalues. Depending on those two eigenvalues, you can compute the stability of fixed points. Okay. So you can analyze why we are spending so much time on 1D systems. Just that you get the basic ideas so that you can generalize when the two-dimensional systems come into play. Okay, so I just gave you an intuitive idea about period doubling bifurcation when it occurs. It occurs when the derivative at the fixed point, evaluated at the fixed point, is -1. Okay, then there the stability is lost. Okay, there the stability is lost, and a period 2 orbit is born. Okay, that's the idea. Okay. Now we will look into a different bifurcation. You might say, like, yes, what is so special at -1? Why it can't be 1? It can be 1 also. Now I will show you if it is 1, it is a new kind of bifurcation. Okay, it is a new kind of bifurcation. So let us see this with an example. Let me call this now, this is known as something known as a saddle node, or also known as a tangent bifurcation. It's a very nice bifurcation, and I'm pretty sure many of you have already noticed this in your class 12th, already noticed this while plotting graphs in class 12th, but you might not have looked into the way now you will look. Let us take this map, just a 1D map. Xn plus 1 is this mu plus xn minus xn square. Okay. So this is just a 1D map, isn't it? Just like the logistic map. It just looks very similar to the logistic map. The same quadratic terms you have. Now, just note this one. We will go to Desmos. We'll go to Desmos now. Okay, we will play around here. Okay. So can you tell me, like, the form I told you, y equals to mu plus, let us say r, mu plus, plus, fine. Okay. Now let us see what happens. Okay, let us draw y equals to x as well. Okay, let us draw y equals to x and let us draw the curve. You already know that where this y equals to x and y equals to the function equation intersect, those are the fixed points of the system. Okay. Now let us see this argument. Now notice two things. R is greater than 1 here. Let us do negative, R to be negative. R is a parameter here. If R is negative, what you see, do they intersect? No. Let us slowly increase the parameter r. It is coming closely. Okay. Now, slowly, if you see, it made a contact very often. Yeah, it made a kind of a contact. It made a tangential contact. It made these two curves made a tangential contact with each other. Now, if I vary more than r equals to 0, if you see, like if I take more than r equals to 0, it's are born. 2 points took birth. Okay. So no, out of nothing, 2 points took birth. So less than r less than 0, there was no fixed point. R greater than 0, there were two fixed points. I'm not commenting about stability here. I'm not commenting about stability here. But there are two fixed points. So you can see out of 0 fixed points, 2 fixed points were born. So this is a qualitative change in the behavior of the system. Okay. So otherwise, 0 fixed point could have stayed. But since this happened, this is known as a bifurcation. Okay. And what kind of bifurcation is this? This is known as a tangent bifurcation. When you see this bifurcation only happened once it made a tangential contact like this. Okay, the moment r is greater than 0, it made into 2 points. Okay, so there are two fixed points here, and no matter how much r you keep on rise it, there are still two fixed points only. It cannot be more than 2. It will be only two fixed points because there are two intersections. Okay. Now the idea is, can we compute the fixed points analytically? Can we compute these two fixed points? Can you compute the fixed points analytically? Then we can comment which one is stable, which one is unstable. Okay. And then we will return back to Desmos and look into it from another angle. Okay. Let us do the computation for this fixed point on paper. Okay. Can you tell me like what are the fixed points for this? Fixed points for the above system, for the above 1D map are given by. Yes. So what you do is just equate mu plus x minus x square equals to x. From this, you can easily see that x square equals to mu, or x1 is mu, x2, x1 star, x2 star, the fixed points minus mu. All good with this? Now I am asking you, now you can see, now you can make a contact in your brain that what were those two fixed points? Okay, what were those two fixed points? One was negative, one was positive. Okay, we'll see this again. I ask you, which one is stable? I determine the stability of these fixed points. Determine stability of these fixed points. What we should do if you want to determine whether x1 star is stable, unstable, or x2 star is stable, unstable, what we should do? Yes, we should compute the derivative at the fixed point. So first step you have to do, suppose this is known as f of xn. Okay, this is f of xn. So what we should do, f prime of x1 star and f prime at x2 star. Compute these two quantities. Okay. Now, what is this quantity giving us? Can you tell me? Fine. Is this correct? 1 minus 2x1 star, that is given as 1 minus 2 into root mu. Okay with this? And what we get from this? Again 1 minus 2x2 star. And this is equals to 1 minus. Fine. Okay with you so far? Now we check which one is stable. So first step is x1 star is stable if mod of f prime x1 star is less than 1. That is implying mod of 1 minus 2 root mu is less than 1. Okay. So what we can get here, is this true? This will be, what do you think? Okay, let us see in another way. Let us see in another way. We are seeing the difficult task first. Okay, that's why. Let us see the next part. X2 star. X2 star, what happens to X2 star? Consider f prime of X2 star. What is the value? It is mod of 1 plus 2 root mu. And this will be greater than 1 for any value of mu. Is it correct? Is it correct? Yes, if mu is negative, then yes, we don't have the fixed point. If mu is negative, we don't have fixed point. So there is no real solution. Okay, that's a good point. So you got the idea. If mu is negative, we saw the two curves were not touching each other or intersecting. That means there is no fixed point. And you can see from this equation also. Mu is less than 0 means root over mu is, so there is no real solution. Okay. So therefore you can see the f prime at x2 star is always greater than 1 for all values of, for any value of mu you take. Fine with you? So therefore what can you conclude from this? You can conclude, since the derivative is greater than 1, so x2 star is always unstable. Is always unstable. Fine with you? X2 star is just minus root mu as from here. So x2 star is always unstable. When x1 star is stable, can you tell me? See, you don't need to consider mu. Do you need to consider all values of mu? No. This is the trick part. Calculation. Okay, you just do the calculation that is needed. Do we need the case of mu equals to 0? No, because there is no fixed point at all. So we need only the case where mu is greater than 0. We only need the case where mu is greater than 0. Okay, so you need to analyze the stability of x1 star when mu is greater than 0 according to this inequality. Now I'm asking you where this condition is stable. Can you tell? So this condition can be written as 1 minus 2 root mu less than 1, isn't it? What I should do next? Can you tell me the mu interval from this equation, this inequality? Please tell me this. Hmm? See, what you are telling, you should think whether it makes sense. Okay, see, you told minus 2 to 0. Okay, I say I accept. Okay, but it cannot be, right? Because you are including negative quantity in your case. But we saw that at negative value, there is no fixed point. This solves this inequality. What inequality satisfies this? What value of mu satisfies this inequality? 0 to 2. What value of mu will satisfy this inequality? So mu should not be there in the answer. Zero 4 can't be there. Okay, let me try to. So 1 minus 2 root mu is less than 1. So what you get from here? 1 minus 1 is less than 2 root mu. 0 is less than 2 root mu. Got it? This one. Now let's look into the other case. Okay. What is the other case? -1 is less than 1 minus 2 root mu. Okay. So let us take 2 root mu on that side, or yeah, 2 root mu is less than 1 plus 1. So root mu is less than 1. So mu is it true? So what you are getting? Okay. Anyway, so we got what information we got from these calculations. What information we got from this calculation is there are two things. What we got is first step is x2 star, which is minus root mu, which will lie on the negative axis, is unstable for any value of mu. Second point is x1 star, which is root mu, is stable for this. Now shall we go back? Shall we go back to our Desmos and see this? So if you see a negative point, it will be unstable. If you see a positive point, it will be stable. And we will vary only till 0 and 1. So yes, you can see here. Let us vary from 0 and 1. Let us take this case. Let us take this case. What I will do is, okay. So this is the plot you saw just right now. Okay. So I will tell you, according to our calculations here, x1 star is root mu, x2 star is minus root mu. So can you tell me which one should be the x1 star? Which one should be? There are two intersections, this one and this one. So according to you, which one should be x1 star and which one should be x2 star? X1 star is below. How many? X1 star is below. Like this point is x1 star. Is it correct? No. Yes. It's not correct. So this is x2 star, that is minus root mu. This is x1 star, that is root mu. Okay. This x1 star was stable. So this is a stable point and this is unstable. Okay. Can you now understand understand the concept going on here? So the fixed point you saw here were two fixed points. One fixed point was stable, another fixed point was unstable, right? This is the case for a particular value of r equals to 0.4. For r equals to 0.4. This is the case. Now what we do, now as I vary r parameter, these points come closer to each other. Because you saw they intersected at a tangent, isn't it? They intersected at a tangent, okay? Yeah. Yeah. So, yes. So let us now decrease the value of r. Let us now decrease the value of r. Yeah. So if you keep on decreasing the value of r, say 0.3, 0.2, you can see they come closer to each other. 0.1, you see they started coming closer to each other. 0.05, very close to each other. 0.1, still close. Okay. So at a point, if you still see, they are very close to each other in the order of 0.1 order. Okay, they are coming close. 0.001, very difficult to identify the points of intersection. So the stable and unstable, they come closer and they collide. Okay, the stable and unstable fixed points, they will come closer, they will collide and annihilate. Therefore, you won't see any fixed point for r less than 0. This kind of dynamics, that is the stable and unstable, they come and collide and destruction of fixed point occurs, is known as saddle node bifurcation. Now you can appreciate what is saddle node bifurcation. Okay. In saddle node bifurcation, the stable and unstable point, they come closer and annihilate and destroy each other. So this stable is also known as a node. This unstable is also referred to as a saddle. So therefore, it's a saddle and a node colliding each other, and a bifurcation is happening. Qualitative change is happening because after the collision there is no fixed point. But before the collision there was two fixed points. Bifurcations are known as saddle node bifurcation. What is even more beautiful here? Is you can identify a condition for saddle node bifurcation through this simple example, which will work for any kind of map, not just this map. Can you tell me here? Similar to the analysis of period doubling bifurcation, you saw the tangent line was making a -1 slope. Now, can you tell me what is the slope in this case? 1. So that's a very, very, very nice concept. Okay. So here, just through a single example, you can feel that, yes, if you just draw a tangent at the point where they collide, this tangent line, let me draw it. So this tangent line makes 45-degree axis and the slope is 1. So this is a condition for the occurrence of saddle node bifurcation. So if here f prime at x star will be 1 for saddle node bifurcation. Makes sense now, right? If the slope is 1, you encountered saddle node bifurcation, and when the slope was -1, you encountered period doubling bifurcation. Okay. This will be generalized. When you consider a two-dimensional system, this will be generalized. You will again see this 1 and -1 again, but in a different context. There the derivative won't be there. Okay. Now we are considering derivative. Why? It's a one-dimensional system. We can take derivative. But if you have two-dimensional systems, that is, there's two variables. What kind of derivative you will ask? Partial. That we will take. And when partial derivative you will take? When you have Jacobian matrix. Okay, so Jacobian matrix plays the role of stability in higher dimensional systems. So that's the case here. R will be, what happens? You're saying what happens when R equals to 1? Okay. If R equals to 1, what happens? If R equals to 1, what happens? Sorry, mu equals to 1. Mu, yeah, we just saw that, yeah. Mu should be less than 1, isn't it? Yeah. So if mu equals to 1, what happens? If mu equals to 1, what happens? See, if mu equals to 1, you have derivative to be, what should be the derivative? 1. But at 1, So when mu equals to 1, what happens? Still 1. No, because it is 1 minus 2. Again, you get 1. What happens? That's an interesting question. So at mu equals to 1, yes, now you have to go back into the loop. Okay, because your derivative is equals to 1. Okay, so it's a non-hyperbolic fixed point that we discussed last class. If it is 1, you have to take the second derivative. Okay, it is these cases we discussed last class. If f prime x is equals to 1, where it went? Yes, this one. If f prime of x is equals to 1, then it's a non-hyperbolic fixed point. Okay, then you need to determine the stability. If the second derivative is not 0, then it is unstable. Okay, if you consider the third derivative and if it is less than 0, it is stable. So you have to take help of second and third derivative in those cases. Third derivative will lead to a constant because it's a quadratic map. Okay, so maybe can you do the calculation and show in the next class for this at r equals to 1? Yeah, just apply this case. It's an interesting question. So therefore, like, this is what, like, this is how you will learn it. This is how you learn. See, I gave that example just to show you the saddle node bifurcation. But after that, I'm not bothered about much of it, just to deliver it. But he went a bit more ahead. Okay, so he asked what happens when mu equals to 1. Okay, in that case, you have to take second and third derivative. Maybe you can tell me after doing it. If you get a proper result or anything, that is an important question. We can ask it. Okay, so you can note it down. Show me in the next class. You can assist him also. Whole class can assist. No. Okay. So you got an idea basically, right? So just note down this question. Note down this question. Note this question. Remind me next class. So okay. So when you learnt about how many bifurcation till now? 2 bifurcations: period doubling and saddle node bifurcation. So saddle node bifurcation, when it occurs, something like a tangent. Okay, something like a tangent. It's fine. What happens in that case? Saddle and node, 2 fixed points come closer. One is stable, one is unstable. Collide and they annihilate. When this happens, when the derivative at the fixed point is equal to 1. Okay, fine. So now we will look into, there are 2 other bifurcations we want to look. Okay, one is known as transcritical bifurcation. It's another surprising bifurcation. It's another surprising kind of bifurcation known as transcritical. Transcritical bifurcation. Okay. So what is transcritical bifurcation? To understand this, let us take another example. So yeah, I will tell you later this one. So this is your map. This is your map. 1D map. I am asking you, what are the fixed points of this map? What are the fixed points of this map? Now you have written it down in your notebook, right? Maybe then you can tell me, we can experiment this in Desmos. Can you tell me y equals to? Good. Is it good? Okay. Yeah. So let us vary R and see what is happening. Let us zoom out a bit. Yeah. So you can see that yes, indeed there is a saddle node bifurcation somewhere. Okay, because you see there is a tangent, and if I increase the value of r, there are two fixed points. Okay, yeah, but you see something else. Okay, so this is the nature of this curve. Okay, you can see that 0 is always a fixed point. Okay, 0 is always a fixed point. So for 0, 0 is always a fixed point. Can you feel that 0 is always a fixed point? You got that equation. Hmm? So therefore 0 is never changing its role. So there is one fixed point which keeps on changing its point, like location. If I go negative, the fixed point goes negative axis. If I go positive, fixed point goes positive, isn't it? Can we do the calculation and admire that? I think, can you tell me what are the fixed points of the map? Analytically compute. One will be surely 0. You just saw through this. One fixed point is surely 0. Now I ask you, what is the other fixed point? Can you compute it? Hmm? Can you tell me the fixed points you got? Computation is taking so much time. What are you doing? Okay, so we got two fixed points. X1 star is 0 and X2 star is mu. Now our job is to compute determine the stability of this fixed point. Determine the stability. So can you tell me what happens to f prime at x2 star modulus? So this is f of xn. So what is f prime of xn? That is df by dx. Yes. So if you take the derivative, this term is linear, so you just get 1 plus mu. Then this term is second order, so 2xn. So if I do f prime of x2 star, that means f prime at mu, which is equals to 1 plus mu. So in place of x, you just put mu. So 1 minus mu. Okay. So 1 minus mu. When this is stable. This is stable if this is less than 1. When this will be less than 1. This way. So minus 1 is less than, this is one inequality. This is another inequality. So mu is less than 2 here, and here mu is greater than 0. So from this, mu should lie in between 0 and 2 for mu to be stable. Okay. Now I ask, now let us compute stability of, this is done. Now let us do the stability of x1 prime. So f1 of x1 prime, f1 prime at x1 star. What is that? F prime at 0. So just put 0 here. 1 plus mu, that's it. Isn't it? Can this be less than 1? Mod of 1 plus mu, can it be less than 1? We will have two cases. We will have two cases. Two cases, mu less than 0 and mu greater than 0. For mu greater than 0, 1 plus mu can never be less than 1. Now for mu less than 0, what happens? If you take mu equals to minus 0.1, then 1 plus mod mu is equals to 0.9, which is still less than 1. So this is true. Okay. If you take mu to be minus minus 2, then it is equal to minus of 1, less than 1, still false. Okay, 1 is less than 1 is false. So if you go more than that, mu equals to minus 3, say, then minus 3 minus 1 minus 3, it is 2. 2 is less than 1 is false. So what are we concluding? What are we concluding? From all these things, what are we concluding? Think. What are we concluding from here? Mu is 0, minus 1 to 0. Then what happens? So you can think along these lines, but what I want you to ask is, for mu less than 0, I want you to tell, for mu less than 0, what happens? X1 star is unstable or stable, X2 star is stable or unstable. For mu greater than 0, X1 star, what happens to X2 star? What? That's what I want to know. For mu less than 0, what happens to X1 star? For mu less than 0. Let us see X2 star. Let us see X2 star for the initial state. For mu less than 0, what is happening to X2 star? It is, we saw that it is stable in between 0 and 2. So therefore, for mu less than 0, it is unstable. It is stable in between 0 and 2. That means anywhere else it is unstable. Which one? No, we got X2 star, I am telling about. X2 star, we just computed that it will be less than 1, the derivative, only if mu is in between 0 and 2. It is wrong. I wrote 0 to 2. Are you saying this is different? Yeah, that is less than 1. But what value of mu will satisfy it to be less than 1? 0 to 2. So apart from 0 to 2, so if I tell mu less than 0, does it lie in between 0 to 2? No. So therefore it is unstable. Isn't it? Now if, what happens to X1 star? For mu less than 0. For mu less than 0, we saw till some point it is stable. Till some point, till some negative x's, as he told, -1, I think. -2, Yes, till -2, right? Yeah, till -2 it should be stable. At -2 it is unstable. At -2 it is unstable. So that means means there is a range in the negative axis till which it is stable. So this is stable for mu belongs to open interval -2 to 0. Agreeing? Fine. Now let us go mu greater than 0. What happens to x1 star? Mu greater than 0, 1 plus mu mod is always greater than 1. This is always greater than 1. So it is always unstable. For x2 star, what happens? Mu greater than 0 till 2 it is stable. Stable for mu belongs to 0 to 2. Can you see something again beautiful had happened? What did happen? Can you analyze what happened here? So the whole theory, whatever we did here is like the what do you call? Yeah, the the main thing is here. Okay, so for mu less than 0, you can see x1 star and x2 star is unstable. For mu greater than 0, x1 star is unstable and x2 star is stable. So it is just like this. It is just like this. I will give you two examples. Are there any friend and enemy here? Are there any enemy of yours here? No. Suppose Mr. Sangamesh and Miss Sweta. Okay. So they are in this room. They are friends. Okay. Say. Okay. So one is enemy. No. Trying to get a good example, but I'm not getting. How can I say this? All hair is black. I could have taken if anyone else hair was some other color. Blue. Okay, let us take one. Yeah, let us not worry. Let us take Mr. Sangamesh and Mr. Jaydev. Okay. So what is happening is in this room, Jaydev is wearing that pink color shirt, and Mr. Sangamesh is wearing black color shirt. Okay. Here in this room, when they go to 44, okay, you see that Mr. Sangamesh is wearing the pink color shirt, and Mr. Jaydev is wearing the black color shirt. Okay. So you see what has happened. So what has happened, like exchange of shirts has happened. Okay. It's a normal thing where when you see the IPL matches, they exchange each other's shirts to show respect. Okay. So the same thing happened here. Same thing happened here. What's the same thing happened here? You see for mu less than 0, when mu is less than 0, x1 star was stable, x2 star was unstable. For mu greater than 0, they exchange their stability just to respect each other. Okay. So you can see x1 star got unstable, x2 star got stable. So here, most importantly, exchange of stability took place in between the fixed points. Such type of bifurcation, is known as transcritical bifurcation. Okay. Such type of bifurcation where there is exchange of stability taking place is known as a transcritical bifurcation. So you know what is a transcritical bifurcation now, I hope. It's a bifurcation where, so what is the bifurcation point? Mu equals to 0 is the bifurcation point. Because for mu less than 0, some phenomena was happening. For mu greater than 0, some other phenomena happened. So at mu equals to 0, transcritical bifurcation happened. Okay, appreciated. Fine. Okay. So, all right. So there is one last bifurcation. There is actually a lot of different bifurcations. As you go deeper into this subject, more deeper, you will get more interesting bifurcations. Okay. And it is still evolving. It is still evolving. Okay. So there is one such bifurcation, one simplest bifurcation, one last one, that is known as a pitchfork bifurcation. Yeah. So let us consider one more example. Only happens with me. Anyway. So this is the map. Okay, this is the pitchfork bifurcation. I'm what I'm doing till now is for each bifurcation, I'm giving you an example of different 1D map. Okay, you will see again a very nice concept behind this. Why I'm taking different examples. So consider this map. Okay, we will see what happens if mu is less than 0. What are the fixed points? Are there any fixed points even, or there are no fixed points at all for mu less than 0? And for mu greater than 0, we want to see what happens, what is the number of fixed points. So I think we shall use Desmos again here. All right, so let us use Desmos. Can you tell me the equation? Y equals to 1 plus R into fine. Okay. So yeah, for R less than 0, or mu less than 0, let us see what happens. Can you see what is happening? For R less than 0, there is just a single intersection, still a single intersection. But the moment, can you predict what is going to happen if I shift the parameter to greater than 0? Are you sure? There are 3 fixed points. Okay. So if there was 2 fixed points, you can easily see that this was saddle node bifurcation at least. From 1 fixed point, like the 2 fixed points are born. But here, instead of from 1 fixed point, you are seeing 3 fixed points are born. Okay, what is happening? Okay, that's the idea we want to see or analyze. So you can see there are 3 intersections, 1, 2, and 3. So there are 3 fixed points when R is greater than 0. But when R is less than 0, there is only 1 fixed point. Okay. So this behavior we want to analyze. So can we go into the computation? So what we saw, when mu is greater than 0, when mu is less than 0, we have one fixed point, and that is the origin. Origin is the fixed point. 0 is only fixed point. Only this is the only fixed point. But here for mu greater than 0, 0 is also there. Then what other fixed points are there that you need to tell me? Can you compute the fixed points for this map? Minus mu. Minus mu or minus? Yes. So these are the 3 fixed points. So for mu less than 0, 0 is the fixed point. For mu greater than 0, these are the fixed points. Can you tell me, can we compute the stability here? Can you tell me the stability? What is f prime? This is f of xn. Okay. Can you tell me what is f prime of xn? F prime of xn is 1 plus mu minus 3 xn square. So at 0, at x star equals to 0, x1 star equals to 0, what is f prime 0? 1 plus mu? Yeah, 1 plus mu. Now the modulus of 1 plus mu, what will happen to it? For mu less than 0. So for mu less than 0, what happens? And for mu greater than 0, what happens? For mu greater than 0, 1 plus mu determinant, the mod is always greater than 1. So therefore, this is always unstable. Isn't it? Agree? For mu less than 0, what happens? For mu less than 0, what is happening? Is it okay? For minus 1, it will be less than 1. The quantity 1 plus mu mod will be less than 1. So, and if it is more than 1, more than minus 1, say minus 1.5, it is still happening. Still. No, until minus 2. So if it is minus 2, you are getting 1. Minus 2.1, you are crossing 1. You are crossing. So this will be stable from minus 2 to 0. If mu belongs to minus 2 to 0, this is stable, isn't it? Else, unstable. Everyone agreeing with this statement? Agreeing? Agreeing? Now let us look into other two fixed points. At x2 star equals to plus mu, plus root mu, which only happens if you have mu greater than 0. So indirectly we will take mu greater than 0. So what is f prime at plus root mu? That is mod of, can you tell? 1 plus mu, fine, minus 3 mu. This is 1 minus 2 mu, but where mu is greater than 0. Where mu is greater than 0. So for mu greater than 0, what happens to 1 minus 2 mu? Hmm. 1. So for mu greater than 0, we have x2 star is stable if uh, mu is to 0 and 1, is it? Else unstable. Can we see at x3 star? Can we see at x3 star equals to minus root mu, which is f prime of minus root mu is equal to same, we'll get, I think, the same thing we'll get. 1 plus mu, again minus 3 mu. So again 1 minus 2 mu. Okay. And again, it will be same thing, x3 star stable as above if mu belongs to 0, 1, else unstable. Is it okay with you? Hmm? So what are we seeing here? What are we seeing here? Hmm? No, if you still see, we have a minus 3x square. So we are putting x equal to minus root mu here. So it doesn't matter because it's a square. So always the minus will be there anyway. And derivative is here. Got it, right? Everyone okay with this one calculation? Any issues, any fault? satisfying? So you see, after it born, like, so what can we say from this? So see that I will draw a bifurcation diagram here. So this is for mu. Let me draw this quantity. This is the mu axis. This is the parameter axis. This is the x. Fine. This is the x. Okay. So you can see when for x1 star equal to 0, yes. So for mu greater than 0, it is always unstable. Let us take therefore carefully. This is mu equals to 0. This is 0. This is the 0th point. For mu less than 0, and take this also 0. Got it? Okay. So below this, these are negative quantities. These are positive quantities. This is 0. And this is a fixed point, isn't it? Maybe blue. Let me denote the fixed point stable as blue. Okay. And unstable in red. So is this true? This is for x1 star. Is this true? How many of you agree? See, I wrote 1, 2, and 3. Based on that, I am drawing this diagram. I want to know, upon the variation of the parameter, how the stability of fixed point is changing. That is my basic idea so far. So therefore, how I will know? I draw a mu on the x-axis and the fixed point on the y-axis. So what I do? So at mu less than 0, I know at mu less than 0, we just saw from here, -2 to 0, it is stable as unstable. So till here, till -2, till -2 to 0, x1 star is stable. Therefore, I have written in blue. The moment it crosses 0, for mu greater than 0, x1 star here is always unstable, is always, yes, agreeing with me? So that I will denote by red and with a dotted line. So for mu greater than 0, we have this unstable characteristic. Observe next that we are dealing with the x2 and x3 now. And x2 and x3 were not born when mu is less than 0. They were only born when mu greater than 0. So for mu less than 0, you will not see any of the points regarding x2 and x3 fixed point, because they never born for mu less than 0. So therefore, we need to only analyze now mu greater than 0 case. Okay. So for mu greater than 0 case, what are we having? For mu greater than 0, x2 star is stable. x2 star is stable. And x2 star, how it looks? Plus root mu. x2 star looks like plus root mu. So how the curve will look? It will look like a parabola in the x mu plane, isn't it? So therefore, you will see this structure now, and they are stable, right? They are stable, isn't it? They are stable. So therefore, I'll draw in blue. Okay. But this is something else. Like this part here, you can think that one is plus root mu. This is x2 star. And this one is x3 star, which is minus root mu. Agreeing with me so far? Minus root mu will be just a mirror copy. And that is also stable. We just showed. x3 star is stable till 1. So this you can say this is till 1. So this is the bifurcation diagram. Okay, for the pitchfork bifurcation. In this bifurcation, see the very important thing here. Here, for mu less than 0, you have one fixed point. But for mu greater than 0, you have 3 fixed points. And that is happening as a pitchfork. Like you saw, like Lord Shiva is holding the Trishulas, isn't it? That's a, and even he's holding something like this. Okay. And even maybe in your Marvel series, you might have seen Aquaman. DC, oh, sorry, yeah, sorry. I made a blunder here. So DC, yeah. In DC, there is Aquaman with this thing, okay, where he draws water. All right. So you can make an analogy with this. So this is why this is called a pitchfork, due to the shape of this. Okay, you can see this is the horizontal version of this one. All right. So we mainly covered today like some most important bifurcation diagrams and different kind of bifurcation structures possible. Okay, what we learned about today? What we learned about today is period doubling bifurcation, saddle node bifurcation, transcritical bifurcation, pitchfork bifurcation for 1D maps. For 1D maps. Now, but these structures, if you see these structures, like let us say to you more about it. So these all things, the bifurcation which you are learning right now, is a local phenomenon. Is a local phenomenon. It happens only in a small region. Okay, we will see that. If you go apart from into larger regions, apart from that, the effect of bifurcation can't be felt. Okay, what do I? If I just take a small example, just take a so what I told you just now is bifurcations are valid locally. Bifurcations are valid locally. Okay. What do I mean by that? What do I mean by that? To understand this situation, consider this map. Xn plus 1 is 1 plus xn minus xn square. All right. Which I think is the same example as which is the same example as we discussed for the saddle node bifurcation. You can check your notes. Mu equals to 1 here. See the example considered in the saddle node bifurcation case. Instead that we just took mu equals to 1 here. All right. Can you tell me like what happens if you start your initial condition to be 10, okay, or which is a large number, and see where the maps are getting converged to, where it converges to. If you do x1, where it goes? You tell me. If x naught equals to 10, what happens? What is x1? 1 plus 10 minus 10 square. Minus 89. Okay. What is x2? Calculators. You need calculators just like numerical methods, but not too much. Like numerical methods were a bit more rigorous, but this is not that rigorous. Just calculations and just. How much? Minus 8009. That's good. What happened is just take this 8 this side, 9 this side, put 2 zeros in middle. Okay. So that's how we get this number. Minus 8009. Fine. Then x3 is 1 minus 8009 minus this one. You can use Google also. Minus 6415. Yeah, 2082. This one. So you can see as I keep on iterating the map. Okay, this is fine. We will not go more. Okay, you can get to feel why we can't go more. Okay, so as I keep on iterating the map, you can see that x say 10,000 so on will be tending towards minus infinity. Fine with you? Okay. So you can see that x naught equals to 10 is diverging towards infinity, but what is the fixed point in this case? What is the fixed point? Check 1 is a fixed point. Yes. And check if 1 is a stable fixed point or not. is one a stable fixed point. What you can do, just compute f of x1 star derivative, just the derivative of that. How much? It will be 1 minus 2x1 star, 1 minus 2. Oh, we are getting 1. Okay. Anyway, so I think you need to take this things, but just I want you to let you know that, yes, just I want to let you know that this system would have stable fixed point, but if you take your initial condition too far from that, then you're diverging. It's not converging. So it's not that how Mr. Sangamesh told last class, like any point you take, if it is stable, it will just converge. No, it has a certain region where if you take those initial condition, it will be approaching that fixed point. If you cross that region, then even if it is stable, no, it won't go. It will run to divergence, like you seeing here in this example. Because you took starting point very far, that is 10, it's very far, I think. Okay, it's very far from your fixed points. So therefore, it is diverging. The further iterates are diverging. If you take 0 0.1, 0 0.51, 1.5, so on, it will be converging to some points. Okay. Through this concept, therefore, I told you the bifurcations you are seeing, everything are local. Okay. If you take my 10, 20, 30 like that, you are considering the full space. So that is a global phenomenon. Okay. So these small things you see, small quantities, 0 0.1, 0 0.8, 1.2, all this nearby, these are local phenomena. Just an idea of scaling I'm giving you. Hmm? All right. So, okay. Hmm? In 10 minutes. Hmm? For today. Yeah, we'll stop here, but that, yeah. So, this is done so far. Soon, next class, we'll start with one-dimensional continuous systems. Okay. 1D discrete systems we just completed right now. Hmm? So, let me see this. Mhm. How to. I did not share it.